Hi, and welcome to the section of the physics tutor. In this section, we're going to use our knowledge of current density that we learned about in the last section and begin to apply it. So the big thing to remember here is just make sure you really understand the concepts and the units. Units in physics, chemistry, and all these courses can really save you. So make sure you understand the units, and we'll see why here in just a minute. First problem says there's a current of 5 amps in a wire for 4 minutes. Okay, and the first part says how many coulombs pass through a cross-section of that wire. And part B says how many electrons pass through a cross-section of that wire. So again, this is really an exercise of really making sure you understand truly what the units really are. And the most important thing is to draw a picture, so let's begin with that. So we have a wire, and I'm going to represent my wire as a really high-tech rectangle like this. So there's a wire, circular of course, so it has a cross-sectional area. The current in this wire, I'm going to represent it with I is equal to 5 amps. That's what we say. And somewhere out here, I'm just going to put it over here, we do this for 4 minutes. So literally, we turn the switch on, we have 5 amps of current flowing through, we let it go for 4 minutes, and then we shut it off. So during the whole time that the 4 minutes was elapsing, we were shoving tons and tons of electrons and letting them propagate through the circuit. That's what the current's doing, it's traveling through the circuit. We want to find out for part A how many coulombs pass through a cross-section of that wire. Well, the first thing you really have to remember is that an ampere is a coulomb per second. That is the definition of an ampere. So an ampere is equal to a coulomb per second. So that's your first real clue right there. So that means that 5 amps is really 5 coulombs per second. So what I'm going to end up doing is setting up a unit conversion here. 5 coulombs per second. That's sort of the first trick. They're not going to tell you that in a problem. They're not going to tell you, hey, make sure you know it's a coulomb per second. That's for you to know that that's what an ampere is. And when we say coulomb per second, that means every single second that elapses, 5 more coulombs of current or of electric charge flow past whatever arbitrary cross-section I choose to look at. All right, so what do we need to do next? We want to find out how many coulombs pass through a cross-section of that wire, right? But what we really need to do is basically multiply. Now that we know how many coulombs per unit time, we want to multiply by the time. And that's going to give us the number of coulombs that actually flowed through over 4 minutes. So what we need to do is realize that what we have here is 60 seconds is 1 minute. And the length of time that we have was actually 4 minutes. Now, why do we set it up this way? Because the minutes cancels with this minute here, the seconds cancel with the second. So the only unit left here is coulombs. So when we set that up, 5 times 60 divided by 1, multiplied by 4, we're going to get 1,200. 1,200 coulombs pass. So what this means is that if I could cross-section the wire like anywhere I want, since it's constant current, I could shut it off and cut it, or if I had a counter, let's say, where I could count coulombs flowing through a cross-section, over a 4-minute period, 1,200 coulombs of charge would pass. So really all we're doing is we're looking at units. We have 5 coulombs per second. That's how many coulombs flowing per second. So we're multiplying that by the time that's elapsed. The only problem is the time that's elapsed is in minutes. So we're setting it up in a unit conversion here so that we're multiplying by the time, but we have this conversion factor wedged in so that the units come out and are taken care of. If we didn't do this, then you could tell immediately from your unit conversion that these would not cancel at all, and so you wouldn't actually get the answer that you were looking for. The second part of the problem says how many electrons pass in that time period. So again, it comes back to units. What we have is we know now that 1,200 coulombs is what is passing in that 4-minute period through a boundary. But what is a coulomb? A coulomb is, since what we're trying to figure out here is how many electrons, what we really want to know is how many coulombs are in an electron. That's going to tell us how many electrons are flowing past there. But we know that. We know that 1 electron is 1.6 times 10 to the negative 19 coulombs. So it's 1 electron is a very small amount of coulombs. Now, it doesn't really matter if we put a negative sign here. A lot of you might look at this and say, well, you missed a negative sign because electrons are negative. But in this case, it doesn't really matter, especially since we're talking about an electric circuit. Because remember, we're pretending that positive currents really, if electrons are flowing one way, then the positive hole current is flowing the other way. So that's what I'm saying. The charges, the magnitude, the sign, what I'm trying to say, the sign of the charge doesn't normally matter, especially when we're just trying to count electrons. So you can say that 1 electron is equal to this many coulombs. If you want to stick a negative there, you can. You're just going to ignore it in your final answer anyway. So what we have here is coulombs canceling with coulombs. And so 1200 divided by this very, very small number is going to give us an answer, 7.5 times 10 to the 21 electrons. That's how many electrons are passing. Think about that, 7.5 times 10 to the 21. That's an enormous amount of electrons passing through a cross-section of a wire in a 4-minute period. And you know why there's that many electrons? It's because electrons are so incredibly tiny. Every atom is so incredibly tiny. And so that's really an exercise in unit conversions, mostly to make sure you understand the units associated with current and with amperes. Okay, our next problem says an ion beam contains 2 times 10 to the 8th doubly charged ions per cubic centimeter, and they're all moving with a speed of 1 times 10 to the 5 meters per second. What is the current density? So it's simply constructed problem. You're just trying to find the current density. So you really need to zero in on what we learned about current density in the last section. The only thing that makes this problem confusing is it's talking about doubly charged ions, and that's kind of confusing. And so, but really what you need to do is visualize in your head what's happening. What it says is we have an ion beam. So that's a fancy word that just means, think about solar wind, right? You've got like this giant kind of tunnel of charged particles moving in space or something like that. Or if you have a laboratory with a vacuum chamber, you might have an ion beam moving inside, but it's not a wire, it's not inside of a wire, it's either in a vacuum chamber in a lab or it's in deep space somewhere. Now we're told how many ions we have, 2 times 10 to the 8th per cubic centimeter. So that's telling us how many ions we have in our beam per cubic centimeter. It's the ion density. But we're also told that they're doubly charged. That tells us that, you remember what an ion is. An ion means you take an electron and you throw it over there that way. What you're left with is a positive ion, right? But when they're doubly charged, that means that it's not just 1 electron that's missing, it's actually 2 electrons that's missing. That is to basically end up telling us what the charge of that ion is. And we'll get to that in just a second, but that's what the doubly charged means. It's telling us how much charge each ion has. And we know that this column, or this long tube of ions, is actually not just sitting there, it's all moving. So it's just moving through space, like a nice tunnel or something like that, and we're given the speed. So what we're trying to find is the current density, which means that, yeah, this mass is moving, but if we could slice this tube in half and just look at the end of it, how many amps per square centimeter is going to be flowing through a cross-section area? That's what the current density is. So again, it's an exercise in unit conversions really more than anything else. Always start with what you know. So let's do that. We know that the current density is equal to the current flowing in any kind of conductor or deep space or anything divided by the area, the cross-sectional area of what it is. But the problem here is we don't know what the current is and we don't know what the area is. So a lot of students will start this and say, well, I have no idea. We're given, you know, ions per cubic centimeter, we're given the speed. I don't know what the current is, I don't know what the area is. So I have no idea how to proceed. But you're given a ton of information, so just continue writing things down until you see a path out. All right? For the units here, just to kind of make sure we know, the units here is amps per square meter. That is the unit of current density, amps per square meter. But we just don't have any idea what either one of these numbers is. So let's write down what we do know then. Let's write down what we do know. We know the following. Never ever leave a test problem blank. Make sure you write down what you know. What we know is we have 2 times 10 to the 8th ions. So I'm going to write it down just like it's in the problem. 2 times 10 to the 8th ions. And what? It's not just 2 times 10 to the 8th ions. It's 2 times 10 to the 8th ions per cubic centimeter. This is saying if I have a cubit, a sugar cube, so to speak, of space, I have this many ions inside of it. Now remember, an ion is a charged atom. It's an atom that has either lost or gained electrons. In this case, we're going to visualize the ion as having lost electrons. How many electrons has it lost? It says it's doubly charged. That means it's lost 2 electrons. So what we want to do here, just to kind of continue working here, let's write down the charge of this guy, because we know that we have flowing charge here somewhere, so we know we're going to end up using that. So what we have is 2 times 1.6 times 10 to the negative 19 coulombs, per ion, I should say. So make sure you write the unit properly. So if we lost only 1 electron for this ion, then the remaining nucleus, along with those electrons, would have a charge of positive 1.6 times 10 to the minus 19 if we lost 1 electron. Because the atom's neutral, if you lose 1 electron, what you're left with is just, you know, 1 little electron charge, but it's positive because we've lost that electron. But if we lose 2 electrons, then we've doubled the charge of the ion. That's why the 2 is here. So what we have here is how many ions per cubic centimeter, and what we have here is the charge of every single ion. So you have to write your units consistently. Ions per cubic centimeter, charge in coulombs per ion, per single ion, because you can see these are going to cancel. That's why I'm trying to get you to realize here. So let me go ahead and do that now, just to see where we are. This ion is going to cancel with this ion. So what I have now is, if I were to do the multiplication, I'd have 2 times 10 to the 8th. I'd multiply all this stuff, so I'd get a number, and my unit of my answer would be coulombs per cubic centimeter, because we've kind of eliminated the ion dependency here because we've done the unit conversion. So if I stop now, I would have coulombs per cubic centimeter. But we know that the unit of current density is something, amps up here, we'll get to that in a minute, but it's per square meter. So I know that I don't want centimeters here. I know that that's not going to be right. So let me go ahead and get it at least into meters. What you're trying to do a lot of the time here is trying to inch your way closer to what you're trying to find. And I'm really doing it this way to show you how powerful the unit conversion method can be. So let's inch our way over to meters. So we have a cubic centimeter here. So what I know is 100 centimeters is 1 meter. I know that 100 centimeters is 1 meter. I know that 100 centimeters is 1 meter. If you know the unit conversion of cubic centimeters to cubic meters, then go ahead and use it. You know, I always get confused doing it. So I know I have, this is basically centimeters times centimeters times centimeters, so I have 3 centimeters, canceling with centimeters times centimeters times centimeters. So I know I'm not going to go wrong here, and I know that my teacher's going to know what I'm doing, because when I have it, like, if I try to do a straight conversion of cubic centimeters to cubic meters, I might make a mistake. This way, I know I'm not going to make a mistake. So if I stop here, then what I'm going to have, let me change colors here, is when I take 2 times 10 to the 8th times 2 times this times 100 times 100 times 100, right? Then what I'm going to have is 6.4 times 10 to the minus 5 coulombs per cubic meter. Now I'm getting closer. I'm not there yet, but I'm getting a whole lot closer. I started out with a bunch of ion talk and a bunch of stuff like that, and I've ended up with something that looks an awful lot like a current density, but it's not quite there. I've got meters in the bottom, but it's cubic meters, so that's not quite right. And on the top, I've got coulombs, but I don't really want coulombs, I want amps. But don't forget, amps is really a coulomb per second. So I need to somehow introduce time into this. I look back at my problem and I see, oh, everything's moving with a speed of 1.5, 1 times 10 to the 5 meters per second. So I've got a unit of meter in there, in that speed, and I've got a unit of second in there, which has got time. So I think that's going to help me. So let me get all the way to the answer, and then we'll come back and revisit kind of how we kind of got here. But let's go ahead and start here. So let's start with this, that we ended up with 6.4 times 10 to the negative 5. The unit I have here is coulombs per cubic meter. This is, if I were to look at this ion beam, then if I could measure it, I would have this many coulombs for every cubic meter of that ion beam. That's what I've calculated up to this point, so never forget what you have. All right, now what do I have? I know the whole thing's moving. It's moving with 1 times 10 to the 5 meters per second. And I orient it this way rather than upside down, because this meter is going to cancel with one of these guys, leaving me with meters squared. And everything else, nothing else cancels. So what I'm going to have here, when I take this and multiply by this, I'm going to have 6.4. And I'm going to have coulombs on the top over seconds here times meter squared on the bottom, because this became meter squared, this was second, this is coulomb. I'm really, really close. Don't forget that, I think you might be able to see the answer now, an ampere is equal to a coulomb per second. It's basically a flow of charge, right? Here I have a coulomb per second. This is what I have here. So really what I've written down is 6.4. I don't even have to do a conversion. This is amps on the top because that's what an amp is. This is square meters on the bottom. This is the unit of current density. So that means that if I could slice that ion beam in half and look at the end of it as everything's flowing out, I would find 6.4 amps for every square meter of the cross section of that ion beam. I would find this many amps flowing through towards me. All right? So this is it. This is the answer. And it's a great, great example of the power of unit conversions. Sometimes in physics, it's a little hard to visualize how to get to the answer. I mean, you can think about this all day and still not know whether you should divide or multiply a lot of times. But the bottom line is you have an ion beam. Think of a tube of charged particles. We're told how many ions are in there, and we're told what their charge is. Even though it doesn't tell you the charge, it says they're doubly charged ions. You got to interpret that to mean it lost 2 electrons. Now we have a positive charge. We have 2 electrons lost. This is the charge of the electrons that left, so this must be the charge of the ion, right? And so we know what the charge of everything is. We know how many we have per cubic centimeter, and we know that they're flowing because they have that guy. So you can kind of imagine like a unit of these ions, and they're moving. So you know that because they're moving, if you could slice it, you would see how many amps were flowing per square meter across the surface area of that little tube of charge that's moving. But still, even though you know that, it might be difficult for you to visualize what you should do with these numbers. And if you get into a case like that, please just try to do some unit conversions, and you'll see that as long as everything you're doing is legal and you're confident that the conversions you're doing are legal, then if you can start with a unit up here and end up with a unit down here, then you have done the problem there. And you can see how complicated this is. We started with ions per cubic centimeter. This is coulombs per ion. Here's a very important thing to make sure that you understand. When you say an ion has a certain charge, it really means that it has so much charge per ion. And then we converted the centimeters to meters so that when we did this math, we started here, but we ended up and we said, okay, this ion beam actually has 6.4 times 10 to the negative 5 coulombs per cubic meter. And we looked at this and we said, well, we're getting closer because the unit of a current density is amperes per square meter. So we started with this, coulombs per cubic meter, and we multiplied by the velocity. You can kind of think of it, you know, almost like density. Whenever you'll take like a regular mass density, you might have a density of something, you know, like kilograms per cubic meter. You multiply by the volume of your beach ball or whatever, how many cubic meters you have, and what you end up with is the mass. Here we started with, it's not exactly the same, but it's similar. We started with coulombs per cubic meter. We multiply by meters every second because this is how many meters are flowing every single second out the end. So when we do that conversion, the meters will cancel, giving us meters squared. The seconds will remain, and what we're going to end up finding is how many coulombs per square meter are flowing, or how many coulombs per second are flowing through a square meter space. And this just happens to be exactly what we're finding, which is the current density, amperes per square meter. So it's very important that you understand the units. That's why I stress it so much in the beginning here. And unit conversions can really, really save you. As long as you know what you're doing, make sure that you're totally legal on all of this stuff. Okay? The next problem is interesting because it's kind of practical. It says we have a fuse in a circuit. And don't forget what a fuse is. It's designed to blow out whenever a certain current is exceeded. It protects your electric equipment, right? A fuse in a circuit is designed to melt, which means open up, when the current density rises to 440 amps per square centimeter. What diameter of wire should be used to limit the current to 0.5 amps at the moment that the fuse begins to melt? At the moment the fuse begins to melt. So basically we have a fuse in a circuit. We know we don't want the current density to ever get higher than 440 amps per square centimeter, which is a unit of current density. This problem is worded in a wordy way on purpose because all physics problems are, but basically what it's asking you to find is what's the diameter of the wire that you need. And it's also telling you that you don't want the current in the wire to get any higher than half an amp. So basically what you're given is you're given the current density that you want to max out at, and you're also given the current the actual current in amperes that you want to max out at. So you need to return to what you know, which is the definition of current density is equal to the current flow divided by the area, the cross-sectional area. So we know that the current density is not going to get any bigger than 440, and the unit of that is amps per centimeter squared, if you forget. Okay? And we also know that we don't want the actual current, the magnitude of the current in the circuit to get any higher than half an amp, right? And of course, the area, right? So what we have is 440, 0.5, and the area there. So just to make it a little bit more clear, since I've got the units there so you know what we're doing, I'm going to go ahead and erase the units here just so that you can just look at the numbers so that we're not getting confused with the A and the A and the A everywhere else. So what we have is this. So if we want to find the cross-sectional area of the wire, right, then we'll just multiply over here to get it over here. And so that the area of this wire, we divide by 440. When we take 0.5 divided by 440, we get 1.14 times 10 to the minus 3, and that's in unit of centimeters squared. The reason it's in units of centimeters squared is because the original problem was our current density was 440 amps per square centimeter. So the unit that we end up with is square centimeters. So really this is the answer. This is just asking us what diameter of wire do we need? And this is the answer. So that's that. But you know, this is really the surface area of the cross-sectional area of that wire. What we're actually asked for is the diameter of the wire. So we need to do a little more work, but it's basically just geometry at this point. We know that the area is equal to pi r squared. So we put this area in, 1.14 times 10 to minus 3, and it's going to be pi r squared. So when we divide by pi, and that'll leave us with r squared, and we take the square root, what we get is 1.9 times 10 to the minus 2 centimeters. This is the radius. And so if the diameter is just going to be double that, so we multiply by 2, we're going to get 3.8 times 10 to the minus 2 centimeters. And you could leave this as the answer, but just to kind of make it a little bit easier to read, let's shift the decimal to 2 spaces, 1, 2, so it's really 0.038 centimeters. And if you wanted to talk about it in millimeters, you just scoot the decimal here, 0.38 millimeters. Because if you're talking about millimeters, then your number has to be a little bit bigger since a millimeter is smaller. So you can write it any way you want. Either one of them's fine. Simple problem, but it just makes you really read and understand what we have here. The current density in the wire is limited to this. The actual current in the wire is limited to this. Once you lock both of those things down, then the area, cross-sectional area of the wire is defined by definition of what the current density is. Once you find the area, then you just convert to a diameter because you know the wire is circular, right? If your wire wasn't circular, then you'd have a different deal, but we basically just assume that all wires are circular in nature. Okay, the last problem here is kind of interesting. It says the solar wind proton density is 8.7 centimeters to the negative 3, and their speed is 470 kilometers per second. Part 1 says, or Part A says, what is the current density? Part B says, if the protons were not deflected by the Earth's magnetic field, what is the current that would reach the Earth? So let's tackle Part A first. We're going to find the current density. Big surprise is what we've been doing so far. But we need to just really make sure we understand. What we're given here is the proton density. So the proton density is 8.7, and then the way I've written it is centimeters to the negative 3. You need to, the way I've written it here is 8.7 centimeters negative 3. But this is called a proton density. So when you do your unit conversion, you need to kind of translate that. 8.7, what do you have? What are you measuring? It's 8.7 protons. Because it's a proton density per centimeter cubed. That's why it's a negative there. And this is just it's just something really honestly to confuse you a little bit. A lot of problems will write it like that. Proton density is 8.7 centimeters to the negative 3. You're like, what does that mean? Why is it negative? Why doesn't it say per cubic centimeters? Well, that's because that's easier to understand. This way, it's forcing you to make sure you know how to write your unit conversion down. So make sure you write it down. How many protons per cubic centimeter? That's all that's telling you. All right? Now, what we want to find is the current density. I know that I'm not going to be wanting to deal with centimeters because current density is amps per square meters. So I want to get rid of that right away. And I have a cubic centimeter, so I know that 100 centimeters is 1 meter. I know that 100 centimeters is 1 meter, and I know that 100 centimeters is 1 meter. And again, if you know the conversion factor of centimeters to meters, then by all means use it. But I just like to make sure that I don't make any mistakes, so I just cancel centimeters 3 times. What I'm going to get on the bottom is cubic meters, and I've done it, and I don't have to look anything up or kind of wonder, is it 10,000? Is it 100,000? I don't have to really think about it. And then finally, this is a proton density, okay, which tells us the charge. It's a proton. So what's the charge on a proton? The charge on a proton is 1.6 times 10 to the minus 19 coulombs per proton. Coulombs per proton. That's the definition. So a lot of times when the students aren't sure how to, they can do this in a unit conversion. You can write anything you want in a unit conversion as long as it makes sense. But you really need to make sure and almost always have something on the top and something on the bottom. A lot of people will say, well, this many coulombs in a proton. Okay, but when you do your unit conversion, you need to be explicit, because what you've done here is you've canceled protons with protons. So all you're left with is, looking through here, you've got cubic meters on the bottom, you've got coulombs on the top. So if I take the 8.7, multiply by 100, of course I'm dividing by 1, so it doesn't do anything, multiply by this guy, then what I'm going to get is 1.39 times 10 to the minus 12. And that is coulombs per cubic meter, because I have coulombs here, cubic meters from this on the bottom. Of course, that's not what I want. That's an intermediate sort of answer. I could continue this unit conversion even farther to get to the answer, but you don't want to make your unit conversions too crazy, because then you won't know exactly where you're trying to go. I know that I started with protons per cubic centimeter, and I ended up with coulombs per cubic meter. And I know that my target unit for current density is the unit of amperes per square meter. But don't forget, an ampere is a coulomb per second. So I'm close. But I know that this proton beam is moving with a speed in meters per second. So 1.39 times 10 to the minus 12 coulombs per cubic meter. That's what I'm starting with again here. And the speed here is 470 kilometers per second. So it's 470 kilometers per second. But this isn't quite right, because I have meters and I have kilometers. But that's okay. I'll just do another conversion here. It's the beauty of this thing. So 1,000 meters is 1 kilometer. I just did a quick conversion here, right? Right in the middle of everything else. So what I have here is kilometers ending with kilometers. And this meter cancels with only one of these guys, so I still have 2 meters squared basically on the bottom. Maybe that's a little bit more clear if I just write it over here, meters squared, right? So what do I have when I do it this way? Now if I flip this over on accident, this 470 kilometers per second, then nothing would cancel at all, so I know I have to write it this way. When I take 1.39 times 10 to the minus 12, multiply by 470, multiply by 1,000, then what I'm going to get is 6.54 times 10 to the minus 7. And what do I have here? It's coulombs on the top from here over seconds from here, and then meters squared, right? But don't forget, a coulomb per second is simply an ampere, right? So what I'm going to have here is 6.54 times 10 to the minus 7. This is amps per square meter. Amps per square meter. And this is the answer. You can circle that. This is a unit of current density in amps per square meter. But it's a really incredibly small number, so it's fine to write it like this if you wanted to. Notice it's 10 to the minus 7. So if we go this way 1, it'll be 10 to the minus 6. So we could write this, if we wanted to be a little bit more concise, 0.654 instead of times 10 to the minus 6, we'll just make it microamps per square meter. This is the current density. Of course, you could leave it like this. It's really the same thing. It's just a lot of times, use your metric prefixes, and that way you don't have to carry through the whole scientific notation everywhere. 0.654 microamps per square meter. So again, this is similar to the other problem we did before. It's really an exercise in unit conversions. And you'd be surprised how many physics problems you can do just by knowing how to do unit conversions properly. So I really recommend that you definitely get comfortable with that if you aren't already. Now the second part of the problem, the final part, is if the Earth's magnetic field were not present, then that means all of these protons coming from the sun, from the solar wind, would be hitting and impinging on the Earth. So the question is, if protons were not deflected by the magnetic field, how much current would reach the Earth? And I'll give you a little bit of a side here. Be very, very thankful that the Earth has a magnetic field, which is generated by the molten core churning all the time. We've got a very stable magnetic field. Of course, it does reverse every few 100,000 years, but more or less it's stable for us anyway on our time scale. But that magnetic field protects us because the solar wind is constantly spewing deadly particles and very high energy protons out all directions in space. But once the charged particles hit the magnetic field of the Earth, they become deflected partly, and they also become trapped. And this is getting a little bit into more detailed stuff we'll talk about later in the course when we talk about the magnetic field. But just for now, just sort of like a curiosity thing for you. The magnetic field tends to like to hang on to these charged particles. It grabs them, and the little charged particles begin to get trapped, and they end up, when I say trapped, they end up orbiting the magnetic field line. So you've probably all seen the magnetic field lines on a magnet, right? So if the solar wind hits them, then sometimes they get deflect off, but oftentimes they get trapped, so they begin to orbit the field lines, and they kind of bounce back and forth from the North Pole to the South Pole of the Earth, orbiting around those lines, traveling all the way from the North Pole all the way down to the South Pole, and they get trapped. But they can't make it through the magnetic field because of the force that the magnetic field exerts on these moving particles, right? So an example of this is basically you have these protons that are trapped, and these electrons that are trapped in the magnetic field line. They're bouncing from pole to pole to pole to pole, and that's what you see in the northern and the southern hemisphere as the aurora, because these charged particles, these protons and these electrons, they're zooming back and forth pole to pole, basically bouncing from pole to pole, can never quite get through. What do you think is going to happen when a high energy proton hits the atmosphere? Because it goes to the other pole before it bounces out and it hits the air. What happens is it excites the atmosphere, kind of like a neon light. There's a tube inside of a neon sign with neon gas in it, and we put electricity in there, which excites the gas. It causes the electrons to begin jumping around, and they start to emit light. Well, these protons from the solar wind are doing exactly the same thing. They're hitting the poles of the Earth because they're bouncing and they're trapped in the magnetic field, and they're going and they're hitting the poles. And when they hit the air at the North Pole and at the South Pole, they literally cause the atmosphere to begin to get excited, just like a neon tube. So you may have seen pictures of the floating aurora, which is kind of shimmering and beautiful. It's all because of the solar wind hitting the atmosphere that's trapped by the magnetic field and bouncing into the poles. So that was kind of an aside. I find it fascinating that this is happening on such a large scale just outside the atmosphere. But if it didn't happen that way, if the magnetic field were not there, every one of those protons coming from the sun would smash into our atmosphere, and basically we wouldn't be able to live here. The radiation would be getting through, and we just wouldn't be protected. So in this problem, what we know is we have 0.654 microamps per square meter coming in from the sun. And what we want to know is, if we didn't have a magnetic field, how much current would be actually hitting the Earth? All right, well, this is again an example almost in unit conversions, but if you can think about it for a second, if you can imagine a tube of charge, let's just say you had the sun is spewing out tons of solar wind, and it's got a huge, huge tube of protons flowing along. But we know inside of that tube that for every square meter of space we have this many microamps. So all we really have to do is figure out what the diameter of the Earth is, right, in square meters. The diameter, the facing diameter facing the solar wind, that's what's going to intercept it in square meters. Multiply how many square meters we have times the current density, which is the amps per square meter. Multiply those numbers, and we're going to get how many amps we have, basically. So the radius of the Earth is 6.38 times 10 to the 6. Right? So the area, what I mean by the area is not the total area of the Earth. I'm talking about the facing area. Imagine the Earth as a circle. It's really a sphere, but we know this radius, which is what we have here. So we want to find out what that facing area is that's kind of intercepting that solar wind. So what it's going to be is pi r squared. Right? So if we take pi and we multiply by the radius squared, then what you're going to get for the radius, or for the surface area of the Earth, or that's the surface area of the Earth, the cross-sectional area that's facing the solar wind, it's going to be 1.28 times 10 to the 14th square meters, right? So this is the cross-sectional area, or the facing area of the solar wind. So really all we have to do is multiply these two numbers together, And really, let's use this number because that will give us the number of amps, because this is in terms of amps instead of in microamps. So in order to find out the current, right, the current A is just equal to this guy, 1.28 times 10 to the 14, and that's in terms of square meters. I'll just write the units down just to make it so we totally understand each other. And we're going to multiply that by the current density of the beam, which is 6.54 times 10 to the negative 7. And the unit of this guy is amperes per meter squared, just to be clear. So you can see the units of meter squared is going to cancel with the units of meter squared here. We're going to be left with amps. And so what we get is actually I wrote the wrong thing down here. What I'm trying to find here is the current. This is the current, I. Okay? And what you're going to get is 8.34 times 10 to the 7 amps. And that is the final answer. The current that would be intercepted by the solar wind hitting the Earth would be 8.34 times 10 to the 7 amps. That's an enormous amount of current. Enormous amount of current. And obviously it has to be because it's the diameter, the cross-sectional area of the entire Earth kind of intercepting all of this current that's being spewed out from the sun all the time. So it's a good problem. Again, you're using your unit conversions, but you're also using some logic. You know that you have this many amps every square meter of your current tube that's coming from the sun. If you know what the area, the cross-sectional area of the Earth is, then you know by multiplying them, you're basically going to get back the current, which is the number of amperes that we have, which is that what we have right here, 8.34 times 10 to the 7. And that's all I have for this section. It's, you could do more problems, but basically they all boil down to definitions and making sure you understand what current density is and how they interrelate to one another. Most of the time when you're dealing with a real electric circuit, like in a circuit theory class, you're not going to worry about current density. You're going to worry about just the current, how many amps are flowing. That's what you're mostly interested in. Current density comes into play more for physics problems, and also if you really have a conductor in a circuit that you happen to know what your current density limitation is, how many amps can it take per square centimeter per square meter of conductor, then you would have to figure all that out in terms of the current density. So it's something you use a whole lot more in physics course to understand the concept. When you really get into an engineering circuits course, you don't really ever talk about current density. You're just normally concerned with how many amps you have running around your circuit.